Functions in Python are reusable, modular components that enhance code efficiency. Higher-order functions, which take other functions as arguments or return them, enable flexible programming patterns. Treating functions as first-class objects allows them to be passed around like data, creating powerful abstractions. These concepts form the foundation for mastering Python's advanced capabilities. Functions are modular components, essential for code reusability. Advanced patterns include higher-order functions, which accept functions as arguments or return them, enhancing flexibility. As first-class objects, functions can be stored in variables, passed as arguments, or returned, enabling powerful abstractions and dynamic programming capabilities. Functions encapsulate reusable logic, utilizing parameters and return values. Variable scope dictates accessibility within function boundaries, with variables existing only during execution. Python's higher-order functions allow passing and returning functions, creating closures and function factories, enhancing modularity and abstraction. Default parameters offer fallback values, enhancing function flexibility. For instance, greet open parenthesis, name close parenthesis, comma, greeting equals quote, hello close. Quote allows optional greetings. Keyword arguments improve clarity by specifying parameters directly, as in greeting hi, name Alice. Variable length arguments using args and aquargs enable handling of dynamic argument numbers, supporting versatile function calls. In Python, functions are first-class objects, meaning they can be assigned to variables, stored in collections, and used as callbacks or decorators. This allows for dynamic invocation and flexible dispatch mechanisms, enhancing programming paradigms. Functions can be stored in lists or dictionaries, enabling powerful design patterns and elegant modifications of behavior. Recursion is a technique where a function solves a problem by dividing it into smaller, similar problems, continuing until a simple base case is reached. This approach allows complex problems to be tackled efficiently by leveraging the simplicity of smaller instances, ultimately leading to a comprehensive solution. Recursion involves a function calling itself to tackle smaller instances of a problem, aiming for a base case to end the process. Imagine Matryoshka dolls. Each open doll reveals a smaller one, akin to Recursion's nested subproblems. Trust the function to solve simpler inputs, then use those solutions for the current input. Recursion relies on two key components, the base case and the recursive case. The base case, like if n equals 0, return 1, halts recursion, preventing infinite loops. The recursive case, such as return n factorial n minus 1, calls the function with a modified argument, ensuring progression towards the base case. Both are essential for effective recursion. Visualizing recursion involves understanding the call stack. Each recursive call generates a new stack frame, holding local variables and execution context. These frames accumulate until the base case is reached. Once the base case returns, the stack unwinds. Processing results in reverse order, crucial for debugging and optimizing recursive functions. Writing recursive functions involves three key steps: identifying the base case, defining the recursive relationship, and ensuring progress toward the base case. Start by writing the base case, then implement the recursive logic. Test with simple inputs and debug by tracing execution manually, adding print statements, and verifying base case handling. In the example of summing numbers from 0 to n, the base case returns 0 when n is 0. The recursive case adds n to the sum of numbers from 0 to n minus 1. Each call reduces n by 1, ensuring termination. The maximum stack depth is n plus 1 frames, illustrating efficient recursion.